So let's start by reviewing the Diffie-Hellman key exchange system. So in cryptography, the problem often is to decide what crypto system to use. Each is determined by some key, by a number. And the standard picture in cryptography is you have two people, two sides, two countries that want to exchange information, and there's someone, Eve, who wants to intercept and understand, find out the message that Alice is sending to Bob or that Bob is sending to Alice. And the problem that the Diffie-Hellman key exchange system solves is this. Let's say your cryptographic scheme depends on some key, some number. And Alice and Bob have to know the number in order to exchange their messages, in order to encode and decode each other's messages. So how do they get this key? So the idea is, the problem was to solve, how do you send the key? How do Alice and Bob both end up knowing the key, but Eve, who's trying to intercept their communications and does intercept every communication, doesn't know what the key is. So this is what is called a public key exchange system. Everybody knows what goes into the system, including Eve, but she still cannot break the system. She can't find the number. So the system is based on, you take a prime number P and an integer G, for example, a primitive root mod P, and you publish P and G. So everyone knows what your prime number is and what your primitive root G is. That's public knowledge. Alice knows it, Bob knows it, Eve knows it. Now, how do Alice and Bob communicate to each other the key that they're going to share, the number they're going to share, in a way that Eve, who intercepts every communication, can figure out what it is? So Alice chooses a secret number A. All right, Alice chooses the number A. She doesn't tell anyone. She doesn't tell Bob. And she lets capital A be the primitive root G raised to the power A and reduce mod P. So Alice can calculate capital A because it's based on her secret number little a. And Bob chooses the secret number little b, and he lets capital B be G to the power little b mod P. Alice sends the number A to Bob. Bob sends the number capital B to Alice, and Eve knows both of these numbers. Let's see, what does Alice do? Alice calculates the number Bob sent her, B, raised to the power A mod P. Alice knows the number little a, that's her secret number. And Bob takes Alice's number A and raises it to his secret number, lowercase b, mod P. And what do we know about B to the A and A to the P? B to the A is G to the B to the A is G to the AB. And A to the little b is g to the a to the little b, which is g to the ab. So capital A to the lowercase b and capital B to the lowercase a, they're equal. So Alice and Bob have both acquired a number that they share. Does Eve know that number? Eve doesn't know the number. Eve knows capital A, and Eve knows capital B. If Eve could solve the discrete logarithm problem, if g to the little a is capital A and you know little a, if she could find lowercase a, the logarithm, she could break their encryption. She would know their secret number. But the discrete logarithm problem seems to be impossible to calculate in any finite reasonable time. That is, given g, you can look at all the powers of g, and eventually you get a. But if the prime p is large, and if the primitive root g is large, this could take 100,000 million years on the fastest computers known. So effectively, this is an unbreakable code. So that's the basis of the Diffie-Hellman key exchange. It's based on the hardness of the discrete logarithm problem. And this is hardness from the point of view of the study of algorithms in computer science. It means that the problem can be solved in finite time, but but even though it's finite, it's exponentially huge, which means in practice, no computer can solve the problem. The sun might burn out before the computer solves the problem. So that's Diffie-Hellman key exchange, and it's based on this discrete logarithm. The Diffie-Hellman key exchange just allows Alice and Bob to communicate a secret number to each other. It allows them to generate a number which they both know and no one else knows. But generating a number is not the same as transmitting a message. And the next serious problem to solve is, how do Alice and Bob exchange a message if everyone knows what the cryptographic system is that they're using? Everyone knows how to encrypt or encode a message, but knowing how to encode a message does not give you the knowledge of the ability to decode the message unless you know the secret key. So one of the first solutions to this problem of public key cryptography was due to the mathematician Elgamal, and I want to describe the Elgamal crypto system. This is what is called a public key crypto system, because you publish to the world the method to encrypt or encode your message. Anyone can encode the message, but the asymmetry in the code is that even though anyone can encode the message, no one except Alice can decode the message. So this is to transmit a message securely. In the Diffie-Hellman crypto system, Alice and Bob end up with a secret number that they share, but that's not a message. That's just a number. That's just some bit sequence. So how do you create the Elgamal public key crypto system? You'll often see the acronym in the book. Public key crypto system is PKC. So whenever you see PKC, that stands for public key crypto system. So you start off by publishing to the world, again, a prime P and a integer G that has very large order mod P. For example, a primitive root, G mod P. So everyone knows this pair P and G. This is public knowledge. Everyone knows P and G. Now, Alice wants to create a way that people can send her secret messages, and only she can decipher, decrypt, decode them. So Alice chooses a secret number, little a, that she doesn't tell anyone else. What she is going to publish is you take the primitive root G to the power A and reduce it mod P. So from her lowercase secret number A, she creates this capital number A and she publishes it. So A is now public. So everyone in the world knows the prime P, the prime G, and this number capital A. So Bob wants to send Alice a message that no one else can understand. So Bob, first of all, he chooses a random number, a random integer or a random element. Let's call it K. He's going to choose K, he's going to use it once and never use it again. So you have this integer K, the so-called random element, and Bob calculates two numbers. So Bob lets C1 be equal to G to the power K mod P. So you take G, Bob takes G, raises it to his number K, and calculates C1, which is G to the K mod P. And he lets C2 be equal to the message he wants to encode. And again, you have to remember, every message, whatever language it's written in, can be transcribed into a sequence of numbers. So C2 is M times A to the K mod P. Capital A is the number Alice published, and this little k, again, is Bob's random element. And what Bob sends to Alice is this pair C1, C2. And everyone can intercept and read Bob's message, that is not his message, but this pair C1, C2. So Bob publishes C1, C2. And Alice needs to decrypt this message. So she decrypt this. The idea is to find the message M that Bob is sending her. So what does Alice do? Alice does the following. So Alice decodes as follows. She has the number, so Bob sends the two numbers, C1 and C2. She takes the first number, C1, raises it to her secret exponent A, and takes the inverse of that, mod P. So that number we can call X. And then she takes X and multiplies the second number that Bob sent her, C2, by X. What is this? X is congruent to C1 to the minus A power times C2, which is M to the A sub K, A to the K. What is this? C1 is G to the K. So this is G to the minus AK times M times A, capital A to the K, but what is capital A? It's G to the power A. So this is G to the AK. These cancel, and we're left with M mod P. So Bob chooses a random number K, random positive integer, random integer K. Let C1 be the primitive root G to the power K. let C2 be his message times the publicly available number capital A raised to the k power. So Bob computes two numbers, C1 and C2. Those are the numbers he publishes. And Alice, who knows her secret number little a, can decode this message to get M. What about someone else who wants to decode the message? How do you get from C1 and C2 to M? Well, I have no idea. You know, C1 is G to the K. The only way to find K, this means that K is the logarithm of C1 to the base G mod P. So to find little k from C1, you need to be able to calculate a discrete logarithm. And no one knows how to do that. And if you don't know how to do that, it's not obvious how you could write this code at all. And it seems to be, given the impossibility of solving the discrete logarithm problem in polynomial time or a reasonably short time, that this is a secure public key crypto system. This is the Elgamal system. And let me work out an example of this so you see it in practice, and because it's easier to study what's in the book. Also, I'll just use example 2.8 from the text. You take the prime P equal 467, and it turns out that G equal 2 is a primitive root mod 467. So Alice chooses for her secret number little a to be 153. So the number she publishes is going to be G to the A mod P. That's 2 to the 153rd power mod 467. And if you calculate that, or if your computer calculates that, this is the number 224 mod 467. So what is publicly known is the prime P, the primitive root 2, and now A, Alice publishes her number, which is 224. If you could find the logarithm of 224 to base 2, that's 153. But again, the effectiveness of the code is based on the apparent impossibility of computing discrete logarithms in a reasonable amount of time. Okay. So Bob has a message he wants to send to Alice. Every message is a number. So let's say Bob wants to send the number M equal to 331 to Alice. So this is the message. So what does Bob do? He computes two numbers, C1 and C2. C1 is G to the K mod P. So Bob, he chooses this random element K. So he calculates G to the K mod P. Let's suppose that he chooses K equal to 197. So that's the randomly chosen number that Bob has picked for this. So what he's sending is 2 to the 197 mod 467. And if you can calculate this, it turns out that this is in fact 87 mod 467. And C2 is going to be the message M times A to the K. The message Bob wants to send is 331. Capital A is the number Alice published. That's 224. And Bob is going to raise that to his secret number K, 147. So when you calculate this, lo and behold, this just turns out to be the number 57 mod 467. So the pair C1, C2 that Bob sends to Alice is 87, 57. And now this is also public. This is what Bob publishes, this pair of numbers, 87, 57. So this is the ciphertext. The plain text, which is the message that Bob is really sending, is 331. That's the plain text. The ciphertext is this pair 8757. So how does Alice decode this pair, decipher, decrypt this pair to find the message? Okay, well, what we said is Alex, so this is how Alice decodes 8757. So we said let X be congruent to C1 to the power A inverse mod P. So C1 is 87. Alice is the only one who knows her secret number, 153. She takes the inverse of that, mod P. And when you calculate this, so mod, what is P? 467. So this is the same as 87 raised to the power 467 minus 153 minus 1. So that is 87 to the 3, 1, 3. So X is 87 raised to the 313th power mod 467. Again, by hand, this is a hard problem. On a computer, it's trivial because these are really small numbers. I mean, big numbers have thousands and thousands of digits. These are 3-digit numbers. So when you calculate this, it turns out this is congruent to 14 mod 467. So X is equal to 14 for Alice. And then how do we get the message? The message M is C1 to the A inverse C2. C1 to the A inverse, that's X. That's 14. C2 is the number 57. 57 times 14 what is 57 times 14? You multiply it together. I'm just doing it by hand. 57 times 14, 228, 57, 897. I get this is 798. And mod 467, this is congruent to 331, mod 467. So Alice finds out that the message that Bob sent her is the number 331. So Alice was able to decipher Bob's message to recover the plain text 331. And no one else can do it, even though they have almost all the information Alice has. Everyone has the prime P, the primitive root G, the publicly announced number capital A, and then the pair of numbers C1 and C2 that Bob sent to Alice. Alice doesn't know and doesn't need to know the random element K that Bob used to prepare his numbers C1 and C2, but she still was able to decipher the message. Anyone who can solve the discrete logarithm problem can decipher the message, but no one knows how to decipher the problem. No one knows how to compute a discrete logarithm in a finite amount of time. So that is this very important Elgamal public key cryptosystem. Let's look at one of the homework problems. This is exercise 2.8 on the Elgamal cryptosystem. So we start with a prime P, 1,373, and we take G equal to 2 as the base for the communication. Alice chooses A equal 947 as her secret number. Her private key. So for Alice, it's 947. And what is her public key? So from the private key, she computes the public key, which is A, which is going to be 2 to the 947th power mod 1373. Now, you can compute this by hand using the power algorithm to compute high powers. Your calculator might not be able to do this, but for example, if you took calculus at Lehman with the calculus lab using Maple, Maple can solve this problem in a microsecond. So I'm choosing to use Maple, which is very good. If I want to know what is the least non-negative residue of 2 to the power 947 mod 1373, Maple gives me the answer. It's 177. So this is the message that Alice publishes. It's P to her secret number A. Yes, it's 2 to her secret number A, 947, mod 1373, and that's 177. Now, Bob also chooses a secret number. His number B that he chooses is 716. That's his private key, and his public key, so that's Bob's private key, and his public key is going to be the number B, which is 2 to the power 716 mod 1373. The book is telling us what that is, but I'm just going to double check using Maple. And we both get 469. Mod 1373. So Alice's public key is 177. Bob's private key, public key is 469. Using Diffie-Hellman, they could exchange now a key using capital A and B. No. But instead, what we want to do is send a message. And Alice wants to send the message 583. So this is part A, this is part B of the problem, and this is a continuation of part B. Alice has a message that she wants to send. She wants to send the message M equals 583. And she chooses a random element for this message, K equal to 877. So she's going to send two messages, C1 and C2. C1 is 2 to the K mod the prime 1373. And C2 is going to be the message M times B to the K which is the message M is 583 and B to the K is, what is B? 469. 469 to the power 877. Mod 1373. So what are these numbers? So 2 to the K, this is 2 to the 877. Mod 1337. Or mod 1373. What is that? I'm just going to use Maple to calculate it. Two to the 877 mod 1373 is 719. And the number C2 is going to be 469 469 raised to the power 877 mod 1373 so this is 583 if my Maple is correct. This number is 644 mod 1373 and 583 times 644. So I multiply that and I look at the least non-negative residue modulo 1373. According to Maple, this is 623 mod 1373. So Alice wants to send the message 583 to Bob. Bob's public key number is capital B, 469 mod the prime 1373. Alice chooses the random element K equal to 877. She's going to send two numbers, C1 and C2. C1 is 2 to the K modulo the prime. That's 2 to the 877 mod 1373. And if my calculation is correct, that's 719. C2, Alice takes her message, 583 times B, 469, to her random element, 877. And again, if this calculation is correct, that's 623. So in this Elgamal cryptosystem, Alice sends the pair C1, C2, which is equal to what? 719 is C1, and 623 is C2. She sends this to Bob. And now Bob wants to decipher this. So what does Bob do? So X is going to be, first Bob calculates. X, which is C1 to his secret number, which is B, inverse mod P. So what is C1? C1 is 719 raised to the power. So C1 to the minus B is the same as C1 to the P minus 1 minus B, which is the same as 719 to, what is P? P is 1373. What is B plus 1? B minus B plus 1. B plus 1, well, Bob's secret number B was 716. This is 717. When you subtract, 13 minus 7 is 6. 12 minus, 13 minus 7 is 6. 2 minus 1 is 1. 13 minus 7 is 6. So this is 719 to the 1616th power mod 1373. And again, I use Maple to compute this. It's the IREM command in Maple. 719 raised to the power 616 modulo 1373. And what I get is X is 995 mod 1373. And C2 in the Elgamal system, sorry, not C2, message M is going to be congruent to X times C2. X is 995, C2 is 623 mod the prime 1373. Oops, I didn't, this is wrong over here. I wrote 1333, it's supposed to be 1373. So 1373 minus 717. 13 minus 7 is 6. 6 minus 1 is 5. This is 656. So I should be raising this to the power 656. And when I raise 719 to the power 656, I get 953. And so my message, in the unlikely event I haven't made any other mistakes, is multiply 953 by C2, which is 623, and reducive modulo the prime 1373. So I'm just doing this on Maple. 953 times 623 modulo 1373. I get 583. What was the message Alice was going to send? $583. It's a miracle I did all the arithmetic correctly, but this is a nice example of encrypting and decrypting using the Elgamal cryptosystem. This is more than exercise B asks us to do, but I wanted to go and actually compute this, give this whole example completely. In part C, Bob is now, see, in part B, Alice sent a message to Bob. In part C, Bob sends a message to Alice, and there the exercise is to decrypt it, but the method is exactly what I used over here. And that's really the guts of this problem. So I think we'll stop right here.